Okay, great. Yeah, so this will be the last talk of this lecture series, and here I'll try to focus on sort of the more positive results, and in particular, I'll try to give a second proof of this integral Hodge conjecture for cubic fourfolds that was featured in Manuela's talks. Okay, so just recall, we define these two groups. C, I guess it should be 4 here. Yeah, which is the, so C4 is the space of integral Hodge classes modulo the algebraic classes. And then C subscript 2 would be the sort of curve classes. So degree 2n minus 2 classes modulo algebraic classes. And these are birational invariants. So we saw some positive results already. This was the theorem of Vincent and extended by Totaro, saying that the integral Hodge conjecture holds for threefolds, which are either uni-ruled or they satisfy some extra conditions, namely that well, either the canonical bundle is trivial and you have this H2 vanishing, or Totaro's extension, which was that the Kodar dimension is 0, and you do have a section of the canonical bundle. Okay, so for threefolds, it's really just sort of one case to look at, which is the degree 4 case, so curve classes. And in that case, we do have some positive results for uni-ruled and yeah, Kodar dimension 0. The proofs here are very, very specific for the threefold case. I mean, they sort of reduce to the 1-1 theorem for surfaces. So the basic idea is the following: you're on a threefold. So if you take some ample divisor and some very high multiple, then yeah, if we take some surface in this linear system, smooth and generic, then by the Lefschetz hyperplane theorem, we know that the push forward map from H2 of S to H2 of X is surjective. So in particular, you know, basically you want to generate classes in here by algebraic classes. So the main idea is that, well, here you have a very, very ample linear system. So there are many surfaces in this family. And there's a sort of variation of Hodge structure argument saying that there are enough deformations of S so that every class in this H2 is the push forward of a 1-1 class on some deformation of this surface S. And of course, this 1-1 class is algebraic. So the whole paper is really just you know, showing this statement here that this family of surfaces moves sufficiently much so that you get 1-1 classes and not just integral classes. Okay, and yeah, one could ask what happens in higher dimensions, in particular what happens for uni-ruled fourfolds. Well, then you have, well, it's easier to make counterexamples just from the counterexamples that you have for threefolds. So you can just take, you know, Collar's counterexample. Well, P1 times that hypersurface is a uni-ruled fourfold, and it's easy to see that the integral Hodge conjecture fails here. So uni-ruled is maybe not the right condition. But also unirational or rationally connected fourfolds have counterexamples. So there's a result by Stefan Schreider, who's here. He he produced an example of a unirational fourfold so that the integral Hodge conjecture fails for codimension 2 cycles. But it's still a sort of very big problem whether for unirational or rationally connected fourfolds that curve classes are generated by, well, algebraic classes, yeah. So this is for codimension 2, but we don't know anything about sort of codimension 3 classes. And maybe in light of these results here, I mean, they are about curves in some sense. So maybe the situation is a little bit better for Z6 here. Okay, any questions about these results? Okay. Yeah, so the main result of today would be a sort of different proof than Manuel's for the integral Hodge conjecture for cubic fourfolds. And yeah, so there are at least 3 known proofs of this result. The first one was, I mean, the result really is due to Claire Voisin. I mean, she proved this a long time ago, and yeah, the first proof used sort of a Lefschetz pencil argument and using normal functions. So the proof I'll present today is with Giovanni Mongardi. I'll use the variety of lines, and it's a little bit different from the one we saw yesterday in Emanuela's talk. Okay, but before we do that, let me just sort of say a little bit more about the Calabi-Yau case. So an interesting question to me is whether the integral Hodge conjecture holds for Calabi-Yau varieties in dimensions at least 4. And here I'm particularly interested in the case where we take so degree 2n minus 2, so that you know, curve classes again. So the answer is probably no for varieties with trivial canonical bundle in general, because it might fail even for abelian varieties. So we already saw some implication of that, because Voisin proved that if the very general cubic threefold is stably irrational, and then this minimal cohomology class is not algebraic on the intermediate Jacobian, which is an abelian fourfold. So of course, most people expect the cubic threefold to be stably irrational, and then that would, by her result, imply that this class should not be algebraic. Okay, yeah, so I wanted to mention sort of, before we move on to cubic fourfolds, I wanted to advertise a little bit for my student who proved the following result, which is sort of it's a statement about Calabi-Yaus in higher dimensions. So it's a very concrete statement. So you take a smooth toric variety, projective, and you take a smooth complete intersection of ample divisors like this, and we suppose that X has dimension at least 3. And well, we also assume that the anti-canonical divisor is an F. So this would sort of fit well with you know, uni-ruled or Calabi-Yau. Yeah. In particular, this, you know, so the anti-canonical could be just 0 here. Okay, then the statement is that the integral Hodge conjecture holds for that complete intersection. So in particular, it holds for all hypersurfaces of Calabi-Yau type in toric fourfolds. And it's a little bit stronger even because this whole H2 is just generated by classes of rational curves. Okay, so it might seem that the conditions here are a little bit restrictive. I mean, after all, it's only about complete intersections, but it's a sort of, it covers a lot of examples, because this is really the main source of examples of Calabi-Yau varieties in general. I mean, even in dimension 3, there's sort of a lot of them. For that reason, these complete intersection Calabi-Yaus have been sort of studied extensively. Okay, so I guess I should be precise and only say that this is for one cycle. So let's see, in degree 2 and -2. So it's a statement about H2. Okay, any questions about this statement? Okay, I'm not going to prove this result, but I would like to give sort of a non-trivial example that shows sort of all the techniques that go into the proof. So the first thing is that we're in a situation where we know sort of the H2 of X, and by the Lefschetz hyperplane theorem, it's isomorphic to the H2 of the toric variety. And luckily, we sort of know that we have, well, we have a nice variety. We have Y, and this is, well, we know that all the cohomology groups here are just generated by classes of torus invariant subvarieties. But there's a sort of more interesting or a more useful theorem here due to Casagrande, saying that the H2 is generated by classes of certain, well, contractible classes. So we say that a class gamma is contractible if there's a toric morphism, well, to some other toric variety with connected fibers, so that, well, this is mapped to a point if and only if the curve is proportional to gamma. Yeah, so yeah, that's a contractible class. And so the idea of the proof is that, yeah, one shows that for sorry, can you hear me? Is the sound on?
Yes.
Yeah.
Okay, great. Sorry. Yeah, so the idea is that for each contraction of this toric fourfold, there should be a curve on X that pushes forward to that corresponding contractible class. So at least that's something a little bit more geometric. So we can interpret the classes in H2 as sort of classes that can get contracted by some morphism, and we need to show that some of those curves actually lie on X. And the proof here is very nice and geometric. So let me explain it in one example. And actually this result, or this example, is very similar to well, the blow-ups in Carolina's talk. So, well, we take some line in P4, and we take, yeah, so say that it's given by x0, x1, x2 equal to 0. Then if we blow up P4 along that line, we get a toric fourfold of Picard number 2. And just by blowing up a line, then, I mean, we know everything about the cohomology here. Basically, we just introduce this exceptional divisor in H2, and in H lower 2, then we introduce a class. This would be a line in the exceptional divisor. So we get one new divisor and one new curve class, and they intersect as follows. So H has degree 1, and E dots this exceptional divisor with -1. So it's similar to just blowing up a point on a predicted space. Okay, so if we compute the canonical bundle, it's given by 5h minus 2e. Yeah, it's not so hard to see that this is base point free. It's ample even. So this y here is a Fano fourfold. Okay, and because it's base point free, it means that x in here, if we take something generic, this will be a smooth Calabi-Yau threefold. And in fact, it's very easy to see what it is. It's just the strict transform of a quintic hypersurface that contains L with multiplicity 2. So it's a blow up of some singular quintic hypersurface in P4. Okay, but because we have these two classes, it's not completely obvious that the integral Hodge conjecture should hold on this X here. All right, so to prove this, we use the birational geometry of Y. So this is a figure. This is the effective cone of Y. So it's generated by E and H minus E. And the Neff cone is generated by H and H minus E. And then the way to prove that this is the case is because we know exactly what the two contractions are. So Y is the blow up of P4 along some line. So we know that there's an obvious contraction, and it's the contraction associated to H. And then we also have another map to P2, which is induced by the projection from the line. So this is a P2 bundle over P2. Okay. Yeah, so and that P2 bundle corresponds to the ray H minus E. Okay, so we know basically everything about the birational geometry of this Y. Okay, but what we're really interested in is X. So X, of course, lives inside here. And yeah, so basically what we have to do is to see what happens when you apply or restrict these two contractions to X. So the first claim is that X contains a curve which has class E. So E is you have the exceptional divisor. Well, you start with L, and you basically blow up L, and which means that you replace L with some P2 bundle over L, and E is just one of these fibers here. So we have to show that X contains one of these fibers here. Yeah, so E is the exceptional divisor, and it's isomorphic to P1 cross P2, in fact. And well, if I restrict the equation or the section of X to this exceptional divisor, I get a 2-3 divisor on this here. And this is easy to compute because we have a formula for the anti-canonical divisor, and X is inside the anti-canonical linear system, so we just compute that it's of type 2-3. But this one we can interpret geometrically. It's any 2-3 divisor inside P2 cross P1 is a conic bundle over P1. Like if you think about the projection to P1, it will, I mean, the fibers there will be plane conics. And yeah, so basically some of those fibers of the conic bundle will split into a union of two lines. And one of these two lines will give exactly such a class that we want. Okay, so we've found at least some line that lies in X, and so we get our claim. Any questions about this so far? Okay, then I'll prove the second claim, which is that X contains a curve which has class H minus E, and this corresponds to this second projection here. Yeah, so what we have to do is to look at this P2 bundle from Y to P2 and restrict it to X. And what happens is that we get an elliptic fibration on this Calabi-Yau threefold. So a priori this is a P2 bundle, and then when you restrict it, you get a plane cubic bundle over P2. Okay, so here we have to actually do something a little bit more involved. You have to sort of use some sort of ampleness, implying that this elliptic fibration here is non-isotrivial, and in fact it's a little bit more than non-isotrivial. In fact, we need that some of the fibers have to split into a union of a conic and a line. So it's not just that you have some elliptic fibration that has some singular fibers, but in fact some of the fibers over this P2 will split into a union of two curves. But then here you get a line, and this line has the class H minus E. So yeah, so we find some sort of curve, namely this line, that represents H minus E, and this lies on X. And yeah, the proof is in general actually very similar to what I just described. I mean, you need some sort of ampleness, positivity to argue for this step here. And then one basically tries to find lines that represents the given classes, and yeah, of course you need lots of toric geometry to do this. So yeah, I think it's pretty nice result with yeah, very geometric arguments. Yeah, any questions about this? Okay, well, in that case, I'll move on to the sort of main result for today. And this will tie in more with the junior talks on irreducible symplectic varieties or hyperkähler varieties. So let me state maybe the big theorem. So if you take a projective irreducible holomorphic symplectic variety of K3n type or generalized Kummer type, then the integral Hodge conjecture holds for 1 cycles on X. So in particular, this group here is 0. And again, the statement is slightly stronger. The semi-group of effective curve classes is generated over Z by classes of rational curves. So in fact, here all of H2 is generated by classes of rational curves. Yeah, and so the main corollary is that the integral Hodge conjecture holds for smooth cubic fourfolds. Right. Yeah. Any questions about the statement? Yeah, so maybe what I didn't say was that, well, what it means for a variety to be of K3n type, it means deformation equivalent to the Hilbert scheme of a K3, not on this on the nose Hilbert scheme.
Maybe I have a question, sorry. If
yep.
X is a moduli space or a Kummer variety, is this statement easier, or is still the same difficulty, or?
I'm not sure I mean, it's certainly easier, like much easier if it is a Hilbert scheme, but a moduli space in general, at least our proof does not seem easier if we know this. Yeah.
Thank you.
Okay, so yeah, and in fact, the proof shows that the second Chow group is just isomorphic to the spatial integral Hodge classes, and this is generated by classes of rational surfaces. Of course, if the cubic fourfold was rational, then you would have lots of rational surfaces, and one could prove that this is sort of obvious. But yeah, at least we get this conclusion here. Okay, let me prove the corollary. So we're going to deduce that the integral Hodge conjecture holds for a cubic fourfold, provided that we know that the integral Hodge conjecture holds for one cycles on the for any irreducible holomorphic symplectic variety of K3n type. This is not so hard, but it uses some nice classical algebraic geometry. So if we take a cubic fourfold, we can look at the variety of lines. And this is a classical fact now that this variety is fourfold of K3n type, K32 types. Yeah, so there is a sort of correspondence between these called the incidence correspondence. So we think about F as lying inside the Grassmannian of all lines in P5. It's the subvariety that parameterize the lines just lying on X. And over F, we have the universal line. So it just consists of line plus point on line, and this maps to both F and X. And here it's a P1 model. Okay, so from that we can define the so-called Abel-Jacobi map, which is a map from H6 of the Fano variety of lines to H4. And what you do is you pull back a class to P, and then you push forward to X. And Beauville and Donaghy prove that this is actually an isomorphism, which is good because this is where our classes live. I mean, so we want to take an integral Hodge class here, and we want to say that it's algebraic, and at least now we know that there's an isomorphism to this H6. Yeah, and this isomorphism, because it's constructed from this correspondence, well, it preserves the Hodge decomposition. So it means that any integral Hodge class is of the form pull back of a curve class and then push forward. But now the point is that, of course, that this class here, gamma, it lies in H33 of F, and by our theorem, we know that it's homologous to a sum of rational curves. So in particular, this is an algebraic class, and so the pullback is an algebraic class because this is just a P1 model, and then the push forward, of course, is algebraic. So that means that the whole class is algebraic, and then we're done. And in fact, the proof shows a little bit more that that we get this statement about rational surfaces, saying that if this is a rational curve, then this is a P1 bundle over this rational curve, so it's a rational surface. And so the push forward here is another rational surface on X. Yeah. Any questions about the statement? Okay. Well, if not, then I'll try to sketch the proof of the main theorem, which is that the integral Hodge conjecture holds for curve classes on K3n type varieties. So yeah, we start with the K3 surface, and now let's define X to be the Hilbert scheme of n points on the surface. So this is a irreducible holomorphic symplectic variety of dimension 2n. So there's a Hilbert-Chow morphism, which sends a subscheme to its support, which lies in the symmetric product. And this morphism here induces, well, it basically tells you how to study the cohomology of this Hilbert scheme. So it decomposes as follows. Well, the H2 is the H2 of the surface plus some class B, and this class B is half of the exceptional divisor of this Hilbert-Chow morphism. And similarly, we have a description of the H2. This is just H2 of S, and then you add one class, which corresponds to a ruling inside the exceptional divisor here. So the exceptional divisor is some, yeah, I mean, it's a bundle over something, and then yeah, you basically get a rational curve here in the fiber. Yeah. Okay, so we know exactly what the, I mean, if you have a Hilbert scheme of n points on the K3, we know exactly how the cohomology looks like. Yeah, and one remark is that the Bovil-Bogomolov form is well, these decompositions here are just orthogonal with respect to the Bovil-Bogomolov form on X. And just a sort of a trivial remark here, the integral Hodge conjecture for one cycle is completely trivial for Hilbert schemes, because well, if I take a Hodge class in here, well, in this decomposition here we have something that's algebraic, and then here we have the 1-1 theorem for S. So yeah, basically we reduce to the integral Hodge conjecture for S, and then that's trivial. So the hard part here is to prove it for all irreducible symplectic varieties that are deformation equivalent to this Hilbert scheme. But for Hilbert schemes themselves, this is a trivial statement. Yeah, any questions? Okay, right. So now, I mean, basically our job now is to produce some curves that should generate the H2. So now we're, instead of looking at just the Hilbert scheme, we take some sort of irreducible symplectic variety of dimension 2n, and let's take a rational curve on X. So I represent that by a map from P1 into X, and I let R be the image inside X. Okay, so then we can take, I mean, we're interested in fourfolds which are deformation equivalent to X. So we consider the whole deformation space of X. And inside there we have the deformation space where we add the class R, and these are exactly the deformations for which this class here stays Hodge type n-1, n-1. So this is called the Hodge locus, I think. Of this class. So it's not the deformations that where you deform the curve, you just say that the class, which is a class in H2, stays Hodge when you deform X. Okay, so yeah, then we use moduli space. So M0X beta will be the Conjecture moduli space of stable maps. It's maps from P1 to X with the property that the push forward of P1 is this class beta. At least this is how the open part of the moduli space looks like. In the boundary, you might need some more components, but you should think of it as just a moduli space which is compactified that parameterizes maps from P1 into X. We associated to this class beta. Okay, so this is a projective moduli space, and we're basically going to use this in the following. And here comes a very useful statement due to Sivran. So the first part is sort of simple. So if there is a component of this moduli space, every component of the moduli space containing this map F has dimension at least 2n-2. Okay, so it's a sort of lower bound on how big the components are. And this is just a dimension estimate. This is what you get from Riemann Roch, basically. Okay, so the first part here is easy. The second one is the more, this is deeper. It says that if there is a component which has dimension exactly 2n-2, so having equality here, then the curve actually deforms in the Hodge locus. So a priori, these deformations here, they parameterize deformations where this class here stays Hodge, but the statement is that if there's one component where the dimension of the component is as small as possible, then the curve itself deforms along with this class. Yeah, so this is Sivran. You should think of this as sort of a it's a statement that goes a little bit in a different direction that what we've seen so far. Basically, you start with a family of say irreducible symplectic varieties, and then you start with a rational curve here. And the statement is that if I just know something about this fiber here, namely that there's a component of this moduli space which has exactly dimension 2n-2, then this curve actually deforms out from this central fiber to cover to cover this T here, provided that this class stays Hodge in the family. So it's a very remarkable thing because here, what we did before was that we took some sort of very general point in the moduli space, and we started with something here, and if it was very general, then you could move it out. But here it's different because here we can take a special variety, and then just knowing this thing about the component means that this curve here actually deforms out to cover sort of other fibers. Okay. Any questions about this statement? Okay. This is very, very useful. So basically, this is going to be sort of the magic of the proof that, basically now we can start with special irreducible symplectic varieties and try to produce rational curves that we know sort of deform out to cover more general moduli spaces. Okay, so now our job is to actually produce rational curves. Yeah, so the goal is to produce rational curves on a Hilbert scheme that deforms in a family of exactly dimension 2 and minus 2. And then if we have that, then we know that they deform in their Hodge loci by the above. So that simplifies a little bit, because now we can work with an actual Hilbert scheme and not just something that's deformation equivalent to a Hilbert scheme. But we need this condition here that that this rational curve should deform in a very small dimensional family, as small as possible. Okay, so here's an example that shows how to construct such curves. So let's take degree 2 K3 surface, and any degree 2 K3 surface is just a double cover of P2. So it sort of looks like you take P2 and you have some equation like this. Oh, yeah, something like this. And yeah, basically, this is a K3 surface which is fibered in genus 2 curves. So if you take a line in P2, the preimage here will be a genus 2 curve. So if I take one of these genus 2 curves, well, it's a hyperelliptic curve. So it has a G12, a linear system of dimension 1 and degree 2. And that's very useful, because that gives us a family of degree 2 cycles. So if I take a point here, then I get 2 preimages. So if I move this point around, then I get a curve of zero-dimensional subschemes of degree 2, and so you get a rational curve on the Hilbert scheme of degree or of length 2 here. So yeah, for each such curve, we get a rational curve on this Hilbert scheme. Okay. Yeah, so that's great, because now we have a rational curve on this Hilbert scheme. We can compute the class. It's not so hard to see that the class, I mean, if we use this basis for the H2 that we had before, namely the H2 of the K3 plus this tau class, then it has the form H minus something. But in particular, it means that this class is a primitive class in H2. Yeah, and to get this coefficient here, you just basically use a geometric argument. Okay, so we know the class, basically. And what we need to check is that this curve here moves in a sort of small family. And in this particular example, it's easy to check because, well, we have a double cover. So we have this pi from S to P2, and the preimages of that map gives you a P2 inside the Hilbert scheme of S. Just, take all the preimages of pi. And the way we construct these curves RC, I mean, they're all going to sort of lie inside this plane. But this plane here is very, very special. The normal bundle of this plane is just isomorphic to the cotangent bundle of P2, which is very negative, so it can actually be contracted by a birational map. Yeah, so that there's a contraction from S2 into some other singular symplectic variety which contracts this plane. but it means that, well, any deformation of this curve RC will have to lie inside P. It cannot move outside this this plane, because the plane gets contracted by that morphism. And from that, we deduce that this curve actually moves in a family of dimension exactly 2, which is 2n minus 2. Okay, so this is what we want. Yeah, and the conclusion is that for any irreducible symplectic variety that's deformation equivalent to this thing here, the integral Hodge conjecture holds, because yeah, you can basically just take that curve and you can deform that out. Yeah. Okay. Yeah. Any questions about that statement?
Sorry, what is the class H on the S2?
Oh, sorry. H is the polarization. So we have a polarized K3 surface of degree 2. So it's the map that, or it's the pullback of the L from P2.
No, I mean the polarization on the Hilbert square.
Oh, so sorry. This is, yeah. This was not. Yeah, it should be some different. Yeah, thank you. It was not the same H. Yeah, thanks. Sorry, you're right. There should be some divisor here, which I haven't specified, that that's ample on this Hilbert scheme. Yeah. Okay. So this doesn't always work. So to get classes on any polarized K3 surfaces, we need to consider singular curves, not just smooth genus 2 curves. And the setup is as follows. If you take a K3 surface of higher degree, you take a curve in the polarization which has delta nodes. And if you have a curve on the normalization of that curve, then you get a rational curve on this Hilbert scheme here. So basically, we do the same thing, but now we consider singular curves, and the linear systems are actually on the normalization of the curve. Yeah. So, but morally, it's the same. So you have some singular curve on S, and generically, well, if you have a G1n, this corresponds to a family of degree n subschemes on this curve, and that gives you a rational curve on this Hilbert scheme. And what you could do is that, well, you can first of all compute the class of the curve you get, and check that it's primitive inside the cohomology group. And the hard part is to prove that the dimension is actually as low as possible, namely 2n minus 1, and 2n minus 2. And second of all, you need to say that you get classes that can sort of reach all the deformations of this Hilbert scheme. Yeah, and for that we use a result by Gilberto and Knudsen. Maybe because of lack of time, I won't go through the details here. I'll just maybe refer to the notes saying that there's some sort of arithmetic condition here, saying that, well, in some cases, we can find such rational curves, or sorry, some curves where there's a G1n, and those curves give us what we want. So there's a whole, yeah, there's a lot of literature on the Brillen-Noether theory of curves on K3 surfaces that we're using in particular, we heavily rely on this result of Giliberto and Knudsen, saying that the curves we want, they do exist. Okay, so let me not focus too much on this thing here, but yeah, I'll put them in the lecture notes. But this is the main idea anyway. We produce rational curves by looking at singular curves on the K3 and linear systems on the normalizations. And then we have to check that this is of the right dimension. Okay. Yeah, and then finally we have to show that for any irreducible symplectic variety of K3 n type, we have enough of these Hilbert schemes so that we can generate any class from rational curves coming from or obtained by this construction. Okay, I wanted to, so yeah, sorry for going a little bit fast in this example here. I really wanted to say a little bit more about sort of open problems, because I think there are quite a lot of interesting things that should be addressed. So one is for rationally connected varieties, yeah, the statement or the question is, if you have a rationally connected variety over the complex numbers, is it true that the H2 is generated by classes of curves? And yeah, of course, you have a rationally connected variety, and the question is whether, you know, you could use those rational curves to maybe generate this H2. Yeah, and this is a very hard problem, I think. There's some results for specific classes of rationally connected varieties, like hypersurfaces in predictive space and stuff like that, low dimensional varieties, but in general it's completely open. And there's a result by Chad Schoen saying that well, if the Tate conjecture holds for divisors on all surfaces, then the answer is yes, I think. So yeah, it's a non-trivial question. Okay, and then we also had the case of abelian varieties that we saw earlier. So if we have an abelian or a polarized abelian G-fold, so this is a primitive polarization, then one can ask about the minimal cohomology class, which is this class here. So it's the theta to the power of G minus 1, and you divide by G minus 1 factorial. And yeah, it turns out that this is an integral class. So of course, it's clear that some multiple of that class is algebraic, but yeah, it's certainly not obvious that the class itself is algebraic. Yeah, so a big open problem is whether that class is algebraic. And as we saw, that there's some relations between these two. To sort of the rationality problems. Yeah, rationality problems for say cubic threefolds. Yeah, and there's also very nice result by Grabowski saying that if this one class is algebraic, then the integral Hodge conjecture holds for all abelian varieties in degree 2n minus 2. So just knowing that one class is algebraic means that sort of basically all classes are algebraic in this H2. Yeah, and the proof is also interesting. It uses this Fourier-Mukai transform. Yeah. There's a couple of more questions. One is for threefolds again. This was asked by Diaz. Is there a simply connected threefold so that X admits a non-algebraic torsion class? So we saw many examples of threefolds where there was a non-algebraic torsion class, but none of them were simply connected. And there are also many simply connected varieties, or threefolds where you have non-torsion classes, namely, Collar's example. But having both of these conditions seems a little bit more subtle. So this is open, I believe. And then I think in the first lecture, we saw this conjecture. If we look at hypersurface in P4 of high degree, well, even there, it's not clear whether the integral Hodge conjecture holds. And this is a consequence of this Griffiths-Harris conjecture. So I think that would probably be a very interesting thing to investigate more, but of course it's a very difficult problem. Okay, so I think basically I wanted to end there. Yeah, I wanted to thank everyone for listening this week. It's been fun to be here at this conference, and particularly I would like to thank all the organizers for organizing this. It's been a pleasure. So yeah, thanks a lot.